Welcome everybody to Algebra 2, Section 3.4, Standard Form of Quadratic Functions and Inequalities. So we've talked so far about absolute value functions and some linear functions. Linear functions we're reviewing from previous units. And now we're going to talk about quadratic functions. So quadratic, the standard form for this is f of x equals ax squared plus bx plus c, where a, b, and c are just coefficients or numbers, and x squared and x are consistently going to just be x squared and x. They're not going to be numbers replacing those when we have our equations. So an example of these, we could see like x squared plus 2x minus 5, or negative x squared plus 3x plus 7, or this could be like a 2x squared or a negative 5x squared or anything of the sort, and they're allowed to be fractions as well. Now, this quadratic equation creates a U-shaped curve called a parabola. So we might recall that a linear function looks like a straight line, an absolute value function looks like a V, and a parabola now looks like a U. And just like absolute value, it can be stretched out wider, it can be made narrower, it can be flipped upside down. All these different things can happen to a parabola just like they happen to an absolute value function. Now it says hey, use your graphing calculator, sketch the following functions. Well, I already went ahead and typed these into my graphing calculator on Calc 84, so I'm going to show the left one first, and then I'll come back and show the right one. So if I type this, so this left one I have typed in my graphing calculator, you see I have it, the top one toggled on, and the bottom one toggled off, on, off. And I go ahead and graph here, and I see my graph here in red, that it creates this U shape. And then we're going to identify some parts of this once we get this graph. So we're going to go ahead and just make a sketch here, noting that the bottom part of this graph, which is going to be our vertex, similar to how we had the vertex of the absolute value, is to the bottom and left, so down and left of the origin. And so I'm going to graph this accordingly, looking something like this. Doesn't have to be exactly perfect, but just something like that. And I want to note here then, as I mentioned, that this is the vertex, and that this dashed line that I'm making right now is what we call the axis of symmetry. Axis of symmetry. And what that means is that across this diagonal, the left and the right side mirror each other. It's like if you were to turn and flip one over the other by going across this line, folding it over that line, it would just fold onto itself. And that's going to be consistently the case where it's going to mirror over itself. Very similar to how the absolute value function did the same thing. Now it's just the U rather than the V. And a lot of times we'll abbreviate, or especially I will, abbreviate the axis of symmetry to AOS. So I often abbreviate it that way. So when you see me write AOS, that's what I'm meaning is the axis of symmetry. Now the axis of symmetry is written as x equals a number. It's written as x equals a number. So I'm going to write that x equals a number for the axis of symmetry. And the reason why it's x equals a number is because it's a vertical line. If we recall, vertical lines are always written in the format of x equals some number. In this case, it's x equals a negative number for this problem. It'd be x equals -1. Now we're going to go ahead and graph this other one here. So going back to my Calc 84, once it loads, going back to y equals, toggling my first one off, my second one on, I go ahead and show this graph. And now this one's opening upside down, and my vertex is up and to the right of the origin. So I'm going to go ahead and sketch this here. Once again, my sketch does not have to be perfect by any means, so it might look something like that, like we just had. Where here, this is the vertex this time, it's way up high. And once again, we have our dashed line that goes through the vertex. Note on both the dashed line goes through the vertex. That will be 100% of the time the case. And we have our axis of symmetry, which I'm abbreviating like I mentioned I would, which once again would be x equals a number. Here it'd be x equals positive 1.5 or 1.5 or 3/2. They're all the same number, just expressed 3 different ways. And we'll go over how to find those actually in just a moment. Now I also want to note here that this vertex here serves as the minimum of this graph, the minimum of this graph. And that just means it's the lowest point this graph ever gets. And this one vertex up here, then you might guess, is the maximum of this graph, which you could abbreviate to max and min if you want. So it's the maximum here. Oh, I almost wrote, I wrote an I instead of a U, silly me. You could write max and min if you wanted as well, like I mentioned here. So this is the maximum because it's the highest point of this right one. And a parabola will always either have a maximum or a minimum, but never both. And the reason why it can't have both here is because these arrows tell us it goes down forever, so it can't have a minimum. And on this first one, these arrows tell us it goes up forever, so it can't have a maximum. And the same is true for for absolute value functions, where we made the b. They also have the vertex being either the minimum or the maximum, depending on whether the parabola opens up or down. And so any parabola that opens up, or any absolute value that opens up, and looks like a normal u or a normal v, will have a minimum, like we see on the left, whereas any parabola, quadratic, or absolute value function, the v, that opens upside down, like we see on the right here, will always have a maximum. Now I want to note that just like when we had the transformations of absolute value functions, we said that this negative here played a factor. That negative tells us whether it reflects vertically, reflects over that x-axis or not. And so whenever the ax squared, when the a is positive, the parabola will open up like a normal parabola, and when there's negative, it'll open down. And the same thing is true with absolute value functions. So that we're seeing a lot of similarities here between absolute value functions and parabolas, and that'll continue to be a theme. Now, that vertical line that divides it into two equal parts, as we mentioned, is called the axis of symmetry. We already covered that. That was the dashed line we said. And we said it's the format of x equals a number. Well, how you find that number is when you're in standard form, you use the formula x equals negative b over 2 times a. So you noticed earlier I said, hey, this is x equals negative 1, or this is x equals positive 1.5. Well, how I found that was I said, okay, if my a is 1, my b is 2, and my c is negative 5, I plug that into x equals negative b over 2 times a, and I said, oh, that's negative 2 over 2 times 1, which is negative 2 over 2, or negative 1. And that's how I knew it was x equals negative 1. The same thing would be true here. I would take x equals negative 3 over 2 times negative 1, and I get 3 over negative 2, negative 3 over negative 2, which is 1.5, as I mentioned a moment ago. My 5 didn't write very well. It's a little bit less bad. There we go. And so that ends up being our axis of symmetry. So we use that to find where the middle of this graph is, and then we want to find the vertex. So how we can find the vertex from there is by plugging this in to the formula. So we plug that in to both x's, and we end up getting our y value out, or the f of x value out, to be the y value of the vertex, and thus we get an ordered pair. It's very similar to how we had with absolute value functions. When we had absolute value functions, we would find the vertex, we'd find the x value of the vertex, which is the same thing as the axis of symmetry. We'd find the x value of the vertex by saying, okay, like f of x equals the absolute value of x plus 2 plus 5. And we'd set what was inside the absolute value bars equal to 0, solve this, and then we say, oh, that's the x value of the vertex. Plug that back in, and then we got our y value out and made an ordered pair for the vertex. Really the same idea, just how we're going about finding it isn't setting the inside equal to 0. It's rather using the formula x equals negative b over 2a. Now, like we mentioned, the turning point is called the vertex. I already covered all this where it talks about the minimum and maximum, and we already labeled those parts in the graph above. So we already did everything with these bullet points. And so now we're going to go down here to these problems where it's asking us to determine whether each function has a minimum or maximum, then find the axis of symmetry and the vertex. So we can know whether these have a minimum or maximum without even graphing them. And that's just by noting that, hey, a is positive here. So since a is positive, it'll open up. And because it opens up, it will have a minimum or a lowest point. Because it goes up forever, it can't have a maximum. And so you could go through and do like a numbers 2, 3, and 4 based upon whether it's the a is positive or negative. Remember, a is whatever's with x squared. Depending on whether a is positive or negative, will tell you whether it's opening up or down, which tells us whether it has a minimum or maximum. Now, if we were to find the axis of symmetry, we mentioned that our formula for axis of symmetry is x equals negative b over 2a. So here, the b is secretly 0x plus 0 for c. So b is 0, so negative of 0 over 2 times a, which is 2 times 4. So as I continue my math here, I end up getting 0 over 8. You can't really have a negative 0, so I just drop the negative. And 0 divided by any other number is 0. So my axis of symmetry is x equals 0. It has to be x equals that number. It can't just be 0, because 0 is just an x value, but x equals 0 is a vertical line, which is what we want. Now, in order to find the vertex, I take that and I plug it back into here. And so I take f of 0 equals 4 times 0 squared. Well, 0 squared is 0, and 4 times 0, last I checked, is also 0. So f of 0 is 0, telling us this ordered pair is the x value we plugged in 0, comma, the y value we got out 0. We're going to move on to number 2 and do the exact same things. So on number 2, because this a is negative, I'm going to clock that right away, I know this is going to open down. And because it opens down, it has a maximum or highest value. And now we're going to find the axis of symmetry. So here, this is a is our negative 1, b is 6, and c is plus 0. Anytime you don't see a part like the b or the c or the a, you'll always see a's on these. Otherwise, they won't have an x squared, and they won't be quadratics. But anytime you don't see a b or a c, those numbers are just going to be 0. So we'll have x equals negative b over 2 times a. So negative 6 over 2 times negative 1, which is negative 6 over negative 2, giving us positive 3. So that's x equals 3. Now taking this and plugging it in to find our vertex, I say f of negative 3 equals negative of 3 in parentheses squared plus 6 times 3. Note this negative is not in the parentheses because the negative is part of the actual function itself. And so now as I plug this in, I end up getting negative 9 because 3 squared is 9, and then I make it negative plus 18. And I end up getting f of negative 3 to equal positive 9. And so this is the ordered pair, negative 3 that I plugged in, the 9 that I got out. Sorry, positive 3. I said negative 3 a lot of places. My apologies, everybody. So this should have been a positive 3 in our function because we got positive 3 for our axis of symmetry. I apologize for anybody I confused there. I probably confused a lot of us there. Let me go back and fix these errors that I made. So I wrote f of negative 3, but I did plug it in as positive 3 still, so I made that part. I did that part correctly, but I didn't write my point as negative 3 rather than positive 3, and so I need to adjust that as well. So now adjusting that, my vertex is 3, 9. Number 3. So here our b is 0 because we don't see any number with an x to the first power. We see an ax squared. We see a plus c because it has no variable. We don't see a bx, so the b is 0. Good to note. Now this does open down since it has a negative there, so it opens down, meaning it has a maximum. And then from there, I'm going to go ahead and find the axis of symmetry. So x equals negative 0 over 2 times negative 2. And the nice part is it doesn't matter what's on the bottom there because we have 0 divided by some number, and 0 divided by any other number is always 0. So the axis of symmetry is x equals 0. Remember, it is important to have that x equals there because it's a vertical line. Plugging 0 in, we like plugging 0 in. It's a nice number to plug in. It makes the math a lot easier than some other numbers would be. We end up getting 0 squared, which is 0, and negative 2 times 0, if you didn't figure that out yet, is 0. And 0 plus 7 is, well, just 7. So f of 0 is 7. So this means that we took 0, plugged it in, and we got 7 out. 0, 7. Moving on to number 4 here, we actually have all 3 parts here listed. No zeros here for A, B, or C. This a is positive, so it is going to open up, meaning it does have a minimum or a lowest value. Finding the axis of symmetry, I'm going to do x equals negative of negative 8. So there's a negative from the negative b over 2a, and there's a negative from the 8 itself being negative. And then 2 times 1 for 2a. And as I continue to do my math, 2 negatives make a positive, so I get 8 over 2. And 8 over 2 is 4. So this is x equals 4. Now I'm going to go ahead and plug this in, and I get f of 4 equals 4 squared minus 8 times 4 plus 9. As I continue to do this math, I get 16 minus 32 plus 9. And as I combine all three of these together, I end up getting the y value of negative 7. So I have f of 4 equals negative 7, meaning my ordered pair is 4 comma negative 7. Moving on, now we're going to start graphing these. And so when we're graphing these, we're going to utilize the same information we've been using so far on the last 4. So we're going to find the axis of symmetry, and from the axis of symmetry, find the vertex, place that in the middle row, and then put numbers up and down, typically just the next integer, increasing and decreasing. And then we're going to plug all those values in and get our y values out, and then graph them. Then we're going to find the domain and range. If this seems incredibly familiar, that's good, because this is exactly how we learned to graph absolute value functions in section 1. We did the exact same thing. We found the x value of the vertex, we put it in the middle row, then we numbered up and down, and then we plugged all those numbers in, got our y values out, and then graphed and did domain and range. We're doing all the same steps. The only difference is how we find that first step, and then the fact that this graph will look like a U rather than a V. And we'll see some other similarities as we go through here as well, like we did on the absolute value function, I should say. So in order to find the x value of this vertex, I'm going to do x equals negative b over 2a. B is secretly 0 here, since I don't have anything with an x. I have negative 0 over 2 times negative 3. That ends up getting me, as it zoomed out on me for some reason, 0 over negative 6, which is just 0. So my axis of symmetry is x equals 0. I could make a dashed line there. I think it's probably a good idea to go ahead and do so, but it's not required to do that, just to be clear. And I'm going to put that right here. And now I'm going to number up and down. So decreasing as I go up, negative 2, negative 1, negative 2, negative 3, and increasing as I go down, 1, 2, 3. So now the table goes negative 3 to 3, with my x value of the vertex being in the middle. And I really could pick any numbers here for x values, as we discussed during 3.1 for the absolute value functions as well. But picking the next integer, the non-decimals, non-fractions, is going to make my life significantly easier here. So now as I plug each of these in, I end up getting the y values of negative 27. If I can write a 2 better, negative 27. It is glitching there for me. There we go. Negative 12, negative 3, 0, negative 3, negative 12, and negative 27. And we're like, whoa, these numbers are big. Yeah, they are. So meaning just the negative 3, negative 2, 2, and 3 are going to go off the graph, and that's okay. We don't have to worry about graphing those then. Now, I do want to note that very similar to absolute value functions, the y values mirrored themselves, going out from 0. So we had negative 3, negative 12, negative 27, and the same things going down. And that is going to be the case for the exact same times that it was the case for absolute value functions, which is whenever this x value of the vertex is halfway between those x values going out. And it's halfway between each pair of x values, meaning these y values are always going to be the same when that's the case. So that wasn't the case when it was a number like 1/3, because 1/3 is not halfway between 1 and negative 1. Or when it was a number like if it was a number like 1/2, excuse me, and it was between 0 and 1, then it would still be symmetrical for the y values, because 1/2 is between 0 and 1. So same thing as the absolute value functions. So now I'm going to go ahead and graph this here. So I have 0, 0 at the origin. -1 comma -3, 1 comma -3, and then by the time it gets to 2, it's all the way down at -12. So these increase or decrease very rapidly. We'll notice with quadratics, they increase and decrease incredibly rapidly here. They start off with a slow increase, and then they get big or small fast. Now this does open down, and we note, I really should fix my U there on the other side. It's not looking much like a U. It's going to bug me. Oh, but I did the same thing. A U there. Okay. We noticed that this was negative at the beginning, so it should open down, which it does. And so we know that, hey, this has a maximum. Even though we're not asked to state it has a maximum, it's good to know. Now for the domain here, the x value is how far left and right it goes. Well, it goes forever left, forever right with no open circles or breaks in betweens. So the domain would be -infinity to +infinity with parentheses on each, or you could also word it as the double-lined R for all real numbers. Just like how absolute value functions always 100% of the time had this domain, quadratics will always 100% of the time also have this domain. Another similarity between the two. The range, though, will change just like absolute value functions did, and we're saying the highest number is 0, but it does go lower, and it goes everywhere in between. So that's -infinity, comma 0, with 0 getting a bracket, because it does actually get to 0. It's a closed circle. Or you could also write it as y is less than or equal to 0, because it's 0 and anywhere lower than it. Moving on to number 6 here. So once again, I start this same way by finding the x value of the vertex. How I do that here is the x-is symmetry, because it's the same thing as the x value of the vertex. So I do x equals -b over 2a. So that's going to be, it zoomed out for some reason, love to see it, x equals negative of -6 over 2 times 1. And that is 6 over 2, which is 3. So I put 3 in the middle, and I'm going to put the increasing and decreasing numbers from there. So 4, 5, 6, 2, 1, 0. And I'm going to start plugging in numbers. I love plugging in 0. Makes my life easy. That's 11, because 0 times all of this is going to be 0. Meaning I'm going to have 11 down here, because this is halfway between the next two. And so I can use that to kind of life hack myself here. So when I plug in 1, I get 6, meaning 5 should also get 6. And I can verify that as well by plugging in 5, and I will in fact get 6. And then I plug in 2, and I get 3, which means that 4 will also give me 3, and it does. The math does work out there. And 3 gives me 2. And so now I plot all these points. So I go to 3, 2, 2, 3, and 4, 3, and then 1, 6, and 6, 5, 6, and then we notice that 0, 11, and 6, 11 go off the graph, and that'll be a very consistent theme, as I mentioned earlier, with these increasing and decreasing quite quickly, that they'll go off the graph a lot of times. So we notice like the gap here from this had a y value change of 1. It went up by 1 and over 1, whereas here that did not happen. It went up by 3, and the next one it goes up by 5 from 6 to 11, and that's going to be very consistent again. So the domain is the same as it always is for these and for absolute value functions as well, which is -infinity to +infinity. And the range is going to be, the other way you can write the domain, I should say, is the double-lined R for all real numbers. The range here, the lowest it gets is 2, and the highest it goes is forever. So from low to high, it's 2, infinity with 2 getting a bracket. And then the other way we could write it is y is greater than or equal to 2 or more. On to number 7 here, finding the x value of the vertex. X equals negative of -8 over 2 times 2. So that is 8 over 4, which is 2. I put that here, and I start labeling increasing and decreasing in integers into my table. And I plot all these points, I plug in all these points, and for the x values, get the y values out, and I get going down the table, 16, 6, 0, -2, 0, 6, 16. Once again, mirroring itself because on the y values, because that this 2 is halfway between the next x values. So now as I go ahead and plot these points, I end up getting this graph. Makes this U, my last ones go off the graph, which is a very consistent theme as we're noticing. It does open up, which the A is positive, so it should have opened up. That's a good sign. It's something you can always use to kind of check some of your work a little bit. The domain would be the negative infinity to positive infinity as always, or you could write it as the all real numbers. And the range is -2 and higher, from low to high. So that'd be -2 comma infinity with a bracket on -2, or y is greater than or equal to -2. Number 8 coming up next, -x squared plus 5. It's negative for the A, so it should open upside down. We'll have to make sure that it does by the time we're done. Now my B is 0 because there's a plus 0x. So as I do x equals -b over 2a, I like that, makes my life easier. So I have negative of 0 over 2 times -1, and 0 over any other number, including -2, is 0. So I have 0 in the middle, and I'm just going to increase and decrease my numbers for the next integer for the x values. Then I plug these in. As I plug them in, I get the y values of -4, -1, +4, 5, and then mirroring on the way down. Then I'm going to go and plot these points. Noting that the points mirror each other over the axis of symmetry. I missed a part of this a little bit. There we go. And that's my parabola. So this time every point was on the graph. How neat. So the domain, -infinity to positive infinity as always, or the all real numbers. The range, the highest is 5, but the lowest is -infinity. So from low to high, it goes -infinity to 5, with 5 being a bracket. Or you could write it as y is less than or equal to 5. On number 9 here, we have a fraction. Woohoo! Okay, we'll talk about what we do with that for our table. That we can make slight changes to if we would like. Don't necessarily have to, but it's a choice you can make. And I would even maybe encourage you to do that to make your life a little bit easier. Once again, definitely not something that's required to do, but it's something that we did do with absolute value functions. But first, let's go ahead and find our vertex, or the x value of the vertex, which is the axis of symmetry. So x equals -b over 2a, which here is negative of -1 over 2 times -1/2. Now, thankfully, since we're multiplying this -1/2 by 2, we won't end up having a fraction on the denominator. So that saves us from having some trouble because it ends up just being -1 on the bottom. And so 1 divided by -1 is just -1. Works out pretty well. Now, while I could pick any numbers here, so I could just pick like the ones I normally do of like 0, 1, and 2, and so on and so forth, I'm going to choose not to do that because if I plug in a number like 1, I'm going to end up doing 1 squared, which is 1, times -1/2 and getting fractions. And while fractions are numbers and we can use them, they show up on the graph just fine as normal as well, especially when you make them decimals. I'm going to want to make my life a little bit easier, even if it means making some of the numbers a little bit bigger. That way my fractions work out just fine. And so I'm going to pick multiples of this denominator. And specifically, I want them to divide or reduce with the denominator well after they're squared. So if I square any even number, such as 0, 2, 4, or -2, -4, and -6, if I square any of these numbers, I'll get another even number, which is then going to make this work out quite well as it reduces with -1/2. And once again, you don't have to do this. You certainly could just do the next numbers, next integers, like we've been doing. So here, as I plug these in, I'll just start with -1, getting me 0.5 or 1/2, which I like to make a decimal when I graph. 0 is going to give me 0, and so does -2. And then 2 gives me -4, and so does -4. And then let me do some quick math here, because I actually did the next integer rather than going by 2's on my own notes. So as I do some math here and figure out what 4 and -6 would be. So this would be -12 and -12. And so now I'm going to go ahead and plot these points. And noticing that 6, negative 12, and 4, negative 12 go off the graph, so I'm just going to not graph them, because I have enough points otherwise that I can certainly make do. And this ends up being my parabola. So here the range is, or excuse me, the domain is negative infinity, infinity, or all real numbers. And the range from low to high is negative infinity all the way up to 0.5. Or 1/2. Oop, I wrote infinity, my apologies. So 1/2 or 0.5, they're the same thing, so I don't care what you write there. And then also you could write y is less than or equal to 1/2 or 0.5. Now if you were to have made the other points, you'd have gotten like -3, which to be compared to making an XY table here, -3, which was -1.5, -1, which is 0. We did -1, my apologies. And then +1, which is also -1.5. So those would have been some different changes there you would have had for just those two being in. And as we plot those, we notice that -3 being with -1.5 would be around here. So that would just slightly change this, but this is already spot on. And so I would just need to edit my parabola a little bit, but this little bit of difference I'm not going to count you wrong for if you already have the other dots, especially on the other points there that we do have here. Now on number 10, we get a piecewise function. How exciting. So piecewise functions, remember, are ones where you stitch together different pieces here. So anywhere that is less than -4 for x values, we're doing this top one, but anywhere that is -4 or greater for x values, we're doing the bottom one. So I like to do this dashed line through here. So x is less than -4, I'm going to make a dashed line there. And x is greater than or equal to -4. So that's where they change from one function to the other. So to the left of this line, we'll be doing the top function, and to the right of the line, we'll be doing the bottom function. Now, even though -4 is not actually part of this function, it's not or equal to the top one. Oh, it just changed my page for some reason. I'm still going to plug in -4 into this function. So as I do so, I'm going to get f of -4 is equal to 2 times -4 plus 5. And that yields or results in f of -4 equaling -3. So this is the ordered pair, -4, -3. Now, because it is not or equal to -4, that's going to be an open circle when I graph it. So I'm going to do an open circle at -4, -3. Now my slope here is 2, so I'm going to use that as 2 over 1, knowing it's going to go uphill from left to right, so I'm going to go down to left 1, because I'm only going to the left, I'm not going up and down here. Next, we're going to go ahead and plug in -4 here as well. You could also choose to do the axis of symmetry, which I will be doing in a moment, but I want to know specifically where it is for this. So as I plug in -4, f of -4 is equal to -4 in parentheses being squared, since what we're plugging in is negative, plus 3 times -4. It is key that I said what's in parentheses, because that ends up being positive 16 minus 12, which is f of -4 equals 4. So that's the ordered pair here, -4, 4. And that'll be a closed circle since this is or equal to -4. So -4, 4. And now I need to make more points. So I can't just use slope to make more points. Unfortunately, I have to actually plug things in. Now, I'm going to make my life a little bit easier, though, to do this by finding the axis of symmetry and thus finding the vertex, and hoping that my axis of symmetry is somewhere over here on this side so I can actually utilize that information rather than being over here. And fortunately enough, it is. I already know that because I've done this problem already. So here, if I do the axis of symmetry, that's x equals -b over 2a, so negative of 3 over 2 times 1, which ends up being -3 over 2, or -1.5. If I plug that back in, I end up getting f of -1.5, or 3 over 2, to end up being -2.25. So I'm going to go and plot that ordered pair, -1.5, comma, negative 2.25. So as I go here, negative 1.5, comma negative 2.25, it'd be approximately there. I'm actually just going to do this in the same light blue I was using. And now I know that it's going to connect to here somehow, some way. And it's going to go this way as well to mirror. And I notice that this is 2.5 away for x value. So 2.5 this way will have the same y value here. So 2.5 that direction would be positive 1. So I'm going to have positive 1, comma 4 as well. You could find the same thing by making a table. So making a table here might not be a bad idea. And doing this negative 1.5 in the middle. And you could do like a negative 1, 0, 1, like we just did, knowing that 1 is 4. And negative 1.5 is negative 2.25. And then going the other direction, negative 2, negative 3, negative 4. Noting that also negative 4 is already 4. And so as I plug in these y values here for this table, I end up getting, or plug in the x values to find the y values, 0, negative 2, and then for negative 1 I get negative 2, and for 0 I get 0. And so now if I continue plotting these points, it's going to make my life a little bit easier here to note where these are. And it's now going to follow these dots, these points I just made. Oops. This does not continue on forever to the left, so I can't go past that point here. I started to, and I realized, oh, I can't do that. And so we have most of a parabola with some of a linear function in the purple. And we successfully graphed our piecewise function. So I still do encourage the use of a table, the use of the axis of symmetry here, plugging in this number into this function and into this function to make my open and closed circles around that. Those can all be the very helpful things. Now here for the domain here, we have forever left, forever right. There is a break in the graph, but at the same x value of this break, we have a closed circle. So everywhere is included in this, and we see this here, that we have the numbers less than negative 4, we have the numbers greater than negative 4, as well as negative 4 itself. So we're not leaving any x values out. So the domain is still negative infinity, comma infinity. It can change with piecewise functions, though, as we've seen before. And it's the all real numbers. The range here, how low to how high, it goes down forever, it goes up to this, but then there's a small break here between negative 3 and negative 2.5, negative 2.25. And so we have to actually make sure we have that break and list this as two separate intervals, one for the purple, one for the blue, because they have a break there. So the purple, I have negative infinity, comma, negative 3 with an open circle at negative 3. So it's a parenthesis at negative 3, U for the union, negative 2.25 where it picks back up with a bracket, comma infinity because it goes up forever. And so from low to high, there is my range. I could also word this as, which I'll do below, the purple part, which is y is less than negative 3, U for union, y is greater than or equal to negative 2.25. Now we're going to move on to inequalities. And just like we noted for graphing absolute value inequalities, quadratic inequalities are going to be the exact same except for two differences. And it's the same two differences we had for absolute value inequalities. Those two differences are going to be the solid line versus dashed line, noting that we're using dashed lines for less than or greater than, and solid lines for less than or equal to and greater than or equal to. So if it has the or equal to, it's a solid line. Otherwise, it's a dashed line. And then shading, that we're going to be shading above or below, depending on whether it's less than or equal to, versus greater than or equal to. So the or equal to tells us whether it's a solid line or dashed line, and whether it's less than or greater than tells us where we shade at the end. Otherwise, the exact same as graphing these otherwise. So we're going to proceed through the same way, finding the x value of the axis of symmetry, which is the x value of the vertex as well. So x equals negative b over 2a, negative 2 over 2 times 1. And so we end up getting this to be negative 2 over 2, which is negative 1. Put that in the middle, make my points below, lower and higher as well. And as I plug these x values in, I get the following y values out. 6, 1, negative 2, negative 3, negative 2, 1, and 6. I plot these points, so I have negative 4 comma 6, negative 3 comma 1, negative 2 comma negative 2, negative 1 comma negative 3, and then I just mirror it on the other side with the other points. Now as I connect these, I have my first of the two differences for inequalities. Because this is not or equal to, this is connected with a dashed line that I'm going to showcase in orange to really highlight this. If it was or equal to, it'd be a solid line. And then my second of the two differences is that because it's greater than, I want the y values that are more or higher than this line. Instead of be up here is shaded in. Now, not over here, because that's technically below the function, because it's going to continue to go up, and eventually that'll be listed as below if we continue to draw it up. So it has to be above here, which is essentially it ends up being inside of it. Number 2, start by finding the axis of symmetry just like we did before. So we do x equals negative b, so negative 4 over 2 times a, 2 times negative 1. So this ends up being negative 4 over negative 2, which is positive 2. Filling out the rest of my table for the x values. That's a positive 1. And then I plug these in and I get the y values of negative 6, negative 1, 2, 3, 2, negative 1, negative 6. And I start plotting these. Oopsie. Oh no, that's not the right spot. I thought I made a mistake, but I didn't this time. This is a solid line since it's or equal to. And then we're going to shade below because these y values are less than it. So it also ends up kind of being inside of it in this case because it's below it. Moving on to number 3 here. The axis of symmetry, x equals negative b over a, so negative 18 over 2 times negative 3, ends up getting me negative 18 over negative 6, which is positive 3. And I fill out the rest of my x values around that. And these end up getting me the y values of very big, or very small technically, negative 22, then negative 7 to 5, and then mirroring it on the other side. So obviously the y values of negative 22 are not going to show up on the graph, but every other one does. And we see some rapid change in this graph where it moves quite a bit between points. And because this is or equal to, it's a solid line here. Let me try that one a little bit less bad. And I'm going to shade above, because it's greater than or equal to, and anywhere out here is technically above it, because as this continues going down forever, it's going to get wider and wider and wider, and so this would technically be above. Now, whether or not you shade in that whole area right there, or you just shade in like up here, I don't care. I get the idea either way that you're shading above. Number 4, x equals negative b over 2a, ends up here being with a b of 0, negative 0 over 2 times 1, which is 0 over 2, and 0 divided by anything is 0, or 0 divided by any other number is 0. I have to clarify that because 0 divided by 0 breaks math and is undefined. But filling out the rest of my table here for the x values, and then plugging each of these in to get the y values. And now I'm going to go and plot these. Obviously, I can't really plot the 15 and the 10 for the y values very well, so I just plot the other 3 points, and I call that good. That'll be sufficient. A dashed line here. Because it's not or equal to, and because it's less than, we're talking about the ones lower and below, which once again technically includes up here and here too, but I'm not going to be a stickler about it. Number 5. X equals negative b over 2a. So here, negative of negative 2, because this is the b. The c is 0, because there's no number without an x, over 2 times a, 2 times negative 2. So this ends up being 2 over negative 4, or negative 1/2, aka negative 0.5. And And I'm still just going to go ahead and do my next integers here. So that's 0, 1, and 2. And going in decreasing numbers, I have -1, -2, -3. Now, because -1 1/2 or -0.5 is still halfway between these next x values, the y values will still be symmetrical on this table. And our y values are -12, -4, 0, 0.5, 0, -4, and -12. And so my graph reflects this here as I plot these points. These being incredibly close together so far, but that's perfectly fine. And then I can't really plot the last ones there because they go off the graph quite a bit. You can try, you can go ahead and be like, they'd be around here, and that's fine. This is a solid line since it is or equal to. And we're going to be shading lower or less than, so below here. And below this graph is underneath any parts of this graph. So inside in this case. Number 6 here. Notice we have that 1/2 again, so I'm going to edit my x values when it's time in accordance to that. But I have x equals negative of -4 over 2 times 1/2. Thankfully, once again, that 2 times 1/2 ends up working out quite well. So I get 4 over 1, which is just 4. Put that in the middle, and I'm going to increase and decrease by 2's here. That way, every number I plug in gets squared and is still even and reduces with this 2, so I don't have fractions. But you could pick, the next numbers such as 5 and 6 and then 7, rather than 6, 8, and 10. As I plug in these numbers, I get the following y values. Obviously, these 4 are going to be hard to plug in, so I just plug in I just plot the other 3. I said plug in, but I meant plot. And then here I have a dashed line since it's not or equal to. And then I'm going to be shading above because it's greater than. And that wraps up section 3.4.